All right, Morgan, here we are again. We're looking at integration by parts again, and we're going to kick it up and do some more things to it, and you'll see that these will be a little longer, but really no more complex, so you'll be fine, and we hope to see you tomorrow. So, all right, let's look at this first example. I laid them out there so I could grab them. Does this show up? I might have to change the chalk.
It shows up.
Okay. All right, so e to the x, well, let me see. It's an x squared first. X squared minus 1, and then e to the x dx. I want you to get used to looking at these kind of problems, like see how, what does number 14, it's gone. Look at what number 16 looks like. So you see what it looks like? There's an expression in x, there's an lx. Sometimes there's an expression in x and then a sine of x or a cosine of x. Sometimes there's an expression in x and then an e to the x. Here is the same kind of expression. So first of all, you need to recognize when to use integration by parts. And always start out checking with u substitution. Because last night there were 2 imposters on that list. So you were looking to, you're going to expect that to check for u substitution first. This one isn't a candidate for u substitution. Can I say u equals anything that's going to help in this case? It really isn't. But at least give it a mental quick look-see. All right, so now we're going to set it up by what we learned yesterday. So we have u and v. E to the x is a nice guy because he fits either. He fits easily into the u box or the dv box. So which way should we do it? Because we have x squared minus 1. Do we want to integrate that, or do we want to differentiate that? In the end, kind of look ahead. You want to have something here that you can differentiate. It's kind of hard on this one to look ahead to see. So we're just going to try one way or the other. What was your suggestion?
I said put e to the x as dv.
Down here? All right. It's really hard to foresee, and we'll just go this way and see where it leads us. We'll know if this times this is something that is integratable or getting closer to something that's integratable. So if you would, Aaron, what is the derivative of x squared minus 1?
2x.
All right, and what's the integral, Aaron, of e to the x?
E to the x.
All right, so using our formula, I don't have it up here. It's uv. So look at where it actually repeated the problem. It doesn't matter, at least the integral sign's gone, so that's a step in the right direction. Minus the integral, I will write it up here, minus the integral of v du. So the integral of e to the x 2x dx. All right, is that something, Gianni, that we can integrate as it stands here?
You could do integration by parts.
All right, but as it is right now, it isn't. So what if we switched it the other way? If we had e to the x here, don't write it out.
Choice.
Don't write it out. If we had e to the x here, Brendan, just kind of go through it mentally, what would be here?
E to the x.
And if x squared minus 1 was here, what would be its integral?
1/3 x squared, cubed minus x.
Right, so this gets much more complicated. It actually raised the exponent, so then we had something x to the 3rd times e to the x, so it made it even worse.
So I did pick right?
So you did.
Yeah.
You did. So how do you know if you picked right or not? Well, the thing is, one thing that did happen here is we went from a quadratic, so this was degree 2 behind the integral sign, to a degree 1. So you're going in the right direction. So if you hit one, you can't integrate it, switch it, at least mentally, and if it looks worse than this one, stick with this one, integrate by parts again. So here we go with box number 2. How you doing there, Jonathan? Can I get rid of some more of this?
Yeah.
Which part? How can I get this?
12, yeah.
Oh, good, that's what I need. Alright. So, Gianni, what am I gonna put in for U and V this time?
You could put in 2x for you.
Alright. So we end up with a 2 here, dx, and an e to the x dx. Oh, no dx. Dx was down here. So the dx is always on the bottom the bottom level, those two boxes. So here's the tricky part. I don't know if you call this tricky, but it's this equal sign. Remember yesterday I said to give it your dirty looks, because this is the day is where it really makes a difference. That negative sign is going to affect everything behind it. What's behind it? It's our integration by parts. It's our uv minus the integral v du. It's going to affect the whole thing. So I'm going to put a bracket there, and my uv is 2x ex, e to the x, 2x e to the x. Make sure that you know that that negative sign is going to affect it.
That is pesky.
Yeah, I know. So minus the integral of v e to the x times 2 dx. All right, so Aaron, clean some of this up for me. I'll rewrite this. All right, distribute the negative sign and take the integral.
Negative 2x e to the x. And then you can pull the 2 out of the integral, so it would just be e to the x would be your integral.
All right,
So minus 2 e to the x.
all right, and then a plus c.
Oh wait, but wouldn't it be positive?
Oh yes, right, because that pesky negative sign. All right, I want to show you another method that you can use for these, and it always works, but I'm sort of timid about showing it to you the first day, because it gets the right answer, but you have no understanding why. At least this formula we developed, and you get an understanding as why. This is called the tabular method, and we're going to do this one again. I only use it when I have to do 2 or 3 integration by parts. So here's the tabular method. You go plus, minus. You always start with a plus. And next to it, you put your u, selection of u from the original problem. What was our u? X squared minus 1. And underneath of that, you're going to take the derivative all the way down till it gets to be 0. So, Brendan, what's the derivative of x squared minus 1?
2x.
And what's the derivative of that?
2.
And what's the derivative of that?
0.
All right, so you're done that column. All right, Gianni, you are going to do the integral. Here's the dv part over here in this column. I want you to do the integrals of e to the x.
It's e to the x.
Okay. Never mind, I'll do it. All right, this was kind of a whippy example. So this table method works like this. You set the table up like this. You always go plus, minus. Then you take your u selection and take the derivatives until it reaches 0. Then you take your integral selection and you integrate it the same number of times. 1, 2, 3, 4 times in this one. So then the answer is, let's see if I can get this right, is only on diagonals. It's kind of funny, you go straight and then you do a diagonal, straight and then a diagonal, straight and then a diagonal. And then this one runs out, so there's no diagonal, so you're done. So how do you read that? Just follow the line. This is plus x squared minus 1 times e to the x. Just following the information along these lines. Then it's minus 2x e to the x. And then it's plus 2 e to the x. Did it work? Did it get what we got?
Yeah. That's really
Do
cool.
that.
It works every time. wants to know what you do.
I wonder how,
We talked
how
about
do people
this-
discover that?
I don't
I
know.
remember talking about like all those weird numbers this morning on Calc.
The
It's
Fibonacci
not really
sequence?
making you think about that.
Alright,
Like,
I don't know how they found it.
The golden ratio?
Jonathan, have you finished this one?
Yes.
Alright, we have one more to
The
do.
golden ratio, Morgan.
Alright,
Remember.
Hi, Morgan.
go ahead and shut this one down so we can start
Bye,
again.
Morgan. Goodbye.
We'll be right back.